So our atmosphere, the air we breathe, is comprised primarily, 78% of it, of nitrogen, 21% oxygen, and almost 1% argon, with a thin slither, what's left of trace gases, 0.03%. When we talk about the composition of air, we mean the uniform stuff, the stuff that no matter where we are in the world, whether it be the driest desert compared to the wettest tropical rainforest, if we take the air component, the dry air component, and analyze its composition, we'll get these same numbers. So this is the stuff that's long-lived, well-mixed, and uniformly distributed and independent of altitude across the globe. But what about our greenhouse gases? The water vapor we talk about, the carbon dioxide and others. How does their distribution in space and time vary? We'll start with what I think is the most important gas, greenhouse gas, water vapor. It's restricted to the lower atmosphere or the troposphere. We saw that through that mixing ratio chart before, that the density of water vapor is greatest at the surface and decreases. By the time you get to the top of the troposphere, there's pretty much no water. It's the largest greenhouse gas by volume, ranging between up to 5% in some parts of the world, typically around the equator, the tropical areas. But its density, its distribution varies highly, spatially and temporally across the globe. Here's an example of satellite-derived atmospheric water vapor. And you can see it's concentrated in red at the tropics. Remember, warmer air can hold more moisture than cooler air. Then as you move to the higher latitudes, further south or further north, we get less atmospheric water in general, but there's regional variations. Consider across the continental US, the East Coast has more moisture in this particular example than the West Coast. So it varies, significantly varies spatially and temporally. Carbon dioxide, another one of the major greenhouse gases. It enters our atmosphere through fossil fuel burning. It's not as bad as it sounds. We need carbon dioxide. If we didn't have carbon dioxide in the atmosphere, plants couldn't photosynthesize and we couldn't eat those plants. So why is it such a problem? It's because we're generating far too much CO2 than our plants and the terrestrial biomes can consume. As measured of May 2019, there was 412 parts per million concentration of CO2 in the atmosphere. I was in Hawaii near Mauna Loa when we broke the 400 threshold, which was a sad day for all the climate scientists that were at this conference. And yeah, it was a significant threshold in many ways, and we've exceeded it. And the question is, how are we going to turn that around? Because our plants cannot cope with this much CO2. Methane, CH4, is another greenhouse gas of significance. Some say it's in terms of trapping the heat emitted from the Earth, it's 100 times more effective than CO2. Methane emissions are primarily from the livestock industry, and as of October 2019, the Earth's atmosphere reached 1876 parts per billion. So you can see that steady increase in the concentrations globally through time there. Nitrous oxide is emitted through microbial activity, primarily gets into the atmosphere by breaking down soils, and soils particularly that have been fertilized. And this too is one of those gases that has far better heat trapping capability than CO2. So greenhouse gases, there's atmospheric water vapor, CO2, methane, and nitrous oxide. While the concentrations might be small, their impact is huge on Earth's climate, and that's primarily because they trap the heat that's emitted by the Earth. You recall that this radiation comes to us from the sun as shortwave, and it's the absorption of these gases and others, and of that shortwave, as well as the stuff that's emitted from the Earth into the atmosphere, a trapping of heat that leads to the warming. And global warming is, of course, not a good thing. But is it all bad? Well, see, ozone is our friend. That's the stratospheric gas that we need to shield us from the ultraviolet light from the sun. Without it, we would burn to a crisp. And so it's a good thing it's there. Its distribution is pretty much peaks around the 20-kilometer mark, so it's right in the guts of the stratosphere. It leads to the heating up of the stratosphere. You might have heard the ozone hole and how during the 1980s there was a big movement to reduce the size of the hole. The culprit there was chlorofluorocarbons that were interacting with solar radiation or inhibiting the absorption capability and leading to a decrease in the concentrations of the ozone around the Antarctic area. But by putting in place an effective protocol, that the hole in the ozone layer has reduced somewhat. And so protocols that politicians put in place can be effective. We have yet to see a similar impact of other protocols on climate. Right, so we talked about gases. Remember from our first lecture on radiation, there's also another constituent of the Earth's atmosphere that plays around with electromagnetic radiation, and that are the aerosols. Aerosols are much, much bigger than gas molecules. There suspended particles in the atmosphere with sizes ranging from 1 or so nanometer right up to 1.1 of a tenth of a millimeter. Their spatial extent and temporal variation varies significantly. They are generally confined to the troposphere. I say generally. Occasionally, through things like volcanic eruptions, we can get pulverized rock getting up to into stratospheric heights. The origin of aerosols varies too. Typically, what we see in Australia is stuff that comes from the middle of Australia, windswept sand or dust from weathered or eroded surfaces, ashes, soot from biomass burning, volcanic eruptions, industrial emissions, but also sea spray. So as waves bash against rocks, the particles that excuse me, are jettisoned from those bubbles that burst and make their way into the atmosphere. And well, they're called maritime aerosols. So here's just a composition of aerosols or aerosol measurement, the optical depth component of atmospheric optical depth due to aerosols. You can see the variation in the intensity over time, and each one of these is a monthly composite over a 10 or so year period. It's quite telling. You can see that the concentrations, the darker reds, is pretty much around the equator here, but it can vary. You can probably speculate as why there might be an increasing concentration over the west coast here of Africa. You might know there's a big pot of sand here called the Sahara Desert, and often winds can transport that sand over the ocean, and so we get these increases local increases in aerosol optical depth, so greater loadings of aerosols in the atmosphere. Play that again just to get the message home. Over some of these more industrial areas too, in China and India, you can see periodic increases, biomass burning over the Amazon jungle here in Brazil. Yeah, so optical depth is a measure of concentration of aerosols, shows the quite significant spatial and temporal variation as an atmospheric component. Aerosols are important in the way they interact with solar radiation, but of course they're also important for weather. For water to transition from gas state into liquid, it needs the right combination of dew point temperature and something to condense onto. That's where aerosols play a significant role in terms of making rain happen. They are cloud condensation nuclei, stuff that rain will precipitate onto or condense onto. Depending on their size and composition, the right combinations of air temperature and moisture, they can lead to rain generation. In terms of the interaction of solar radiation, aerosols have a scattering of radiation back into space, but also through the idea of creating more clouds for rain generation, they can scatter, reflect light directly back into space. And this is suggested as a way of we can end up with global cooling, or rather, let me say that again. There's some suggestion that aerosols can play a part in mitigating the influence of global warming by generating more clouds and reflecting more sunlight back into space, leading to a sort of net cooling effect. The balance, however, between global warming and the role of aerosols in global cooling is still debated. But we know, though, as we increase the amount of cloud cover, the more stuff gets reflected back into space. This increases the planetary albedo, and you'll recall that it leads to a general cooling. So recall from our first lecture that radiation that's not scattered, reflected, or absorbed by the atmosphere finally makes its way to the Earth's surface. The properties of the Earth's surface that determine whether the radiation that gets there is absorbed or reflected is known as albedo. Albedo then tells us how much light, sun's light, gets reflected from the surface back up into the atmosphere. The property of the Earth's surface that determines how much radiation is radiated or emitted back up into the atmosphere is its emissivity. So you have all that shortwave radiation getting down to the Earth's surface, being absorbed by the Earth, then being emitted as long-wave radiation. The amount that gets emitted out of the possible amount that could be emitted is called emissivity. We talked about this in the other lecture too. So different surfaces have different albedos. If you look at all the individually reflected elements of radiation across the spectrum of shortwave radiation, you'll see that let me start that again. Albedo is the integral of the individual spectral reflectance across all the wavelengths of the shortwave region, the electromagnetic spectrum. Typically, we talk about a shortwave albedo. So that ranges everything from about 0.3 microns up to about 3 microns. All that reflected radiation is called albedo. Different surfaces have different albedos. So here's just a catalogue of some of them. Clouds, high albedos as high as 0.95. Snow, again, up 0.75. you'll start to see that this sort of ordered that grasses and clays and stuff, you can get albedos down to about 0.1. For some surfaces like deep water bodies, you can get even lower than 0.05 or so. Yep, so making that point again, that different surfaces have different albedos. So that means they will reflect sunlight by different amounts. Similarly, different surfaces have different emissivities. Now recall, that's the ratio of the amount of radiation that is emitted by a material compared to how much it absorbs. Perfect black bodies emit 100% of what they absorb, but most objects in the world store some energy. So that means the emissivity is less than 1. They don't emit everything they absorb. Here again, a catalogue of some surfaces and their various emissivities. You might remember back in, we were talking about the planetary albedo and the planetary emission. On average, across all the land cover types, clouds and the atmosphere, the emissivity of the Earth is about 0.6. Compare that to some of the values you see here. Right, so and you also recall that the stuff, the radiation that finally gets to the Earth's surface can be partitioned into the net shortwave and net long wave to give us the net radiation at the Earth's surface. We introduce our concepts of albedo in here. At this point, we can write net shortwave is equal to 1 minus the albedo multiplied by the downwelling shortwave radiation. Similarly, in the long wave component of radiation, we model that as using Stephan-Boltzmann's law that we saw earlier lectures, where the emissivity of that surface is here. We've got the Stephan-Boltzmann's constant, and then we have the temperature of that surface. So the net long wave can be written as net downwelling long wave minus the stuff that's emitted, which we represent as emissivity, times the temperature and Stephan-Boltzmann's constant. So that means net radiation can be written like this. The reason we want to write it like that is because we don't have to measure separately downwelling and upwelling if we know the properties of the material. So in the case of shortwave radiation, we know a patch of land, patch of grass, for example, has a albedo of about 0.2. Then all we need to measure is the downwelling shortwave radiation, and we know then 30% of that, or 20% rather, is going to be reflected back. So that means as far as net shortwave radiation available for things like photosynthesis, we've got 80% of the downwelling shortwave radiation. Similarly in the long wave. So it's really about trying to know enough about the surface to quantify how much energy is available to make moisture transport or energy transport from the surface back up to the atmosphere. Now that transport of moisture and energy between the Earth's surface and the atmosphere, and even back again, is called land-atmosphere interactions. When we talk about moisture and energy, we consider we can break this up into the energy that goes into making moisture transport or move from one area to another. That's what we call the latent heat fluxes. It brings the moisture into the atmosphere. The stuff that's available to heat up the atmosphere is what we call sensible heat. And you recall there's that component of radiation that gets stored. So we talk in the first instance up here in terms of radiation balance. This is often called energy balance, but they are equivalent. So if you could measure, or if you knew through methods of remote sensing or other measurement techniques, some of the properties of the Earth's surface, you can write the net radiation in terms of what we can observe and measure. and then break that up into the energy components, the stuff that leads to evaporation, the stuff that leads to heating the overlying atmosphere, the stuff that heats up the ground. We focus on different land surfaces and their environments around it. I've talked about evaporation. So the combined effect of evaporation and transpiration, now that's the emission of, escape of moisture from the leaves in the canopy of trees and plants into the atmosphere by having their pores open and the exchange of CO2 for oxygen and water. That transpiration and evaporation, the conversion of puddles of water into water vapor, the combined effect of the evaporation and transpiration is called evapotranspiration. Now you can consider an environment like a desert where there's probably not much water around. So all that energy that comes to heat up the surface is just going to go back into heating up the overlying atmosphere. However, over a nice well-watered surface, you can have that energy converted into evaporation. So proportionally, you might get a kind of cooling effect. You might have heard of evaporative cooling. So in hot desert areas where, beg your pardon,